Hi, this is the third week of the TA practice. Uh, so we are dealing with the chapter 3 now, and only for the discrete random variable. So I heard that you learn about the what is random variable, and especially for the discrete random variable, and as well as the other distribution like binomial or Poisson distribution. So in this T class, we are going to visualize or see some result from each distribution. So, and especially for getting the probability of each distribution, which is the most important thing for this week T practice. So as already know, discrete random variable has discrete value actually. So we call the probability distribution as PMF, which is the abbreviation of probability mass function here. And we also have discrete graph, like when we visualize the probability of discrete random variable. So when in the first part of the chapter 3, our file has the R command for visualizing the discrete random variable. So after storing our own vector, which is a event x and each probability along with the x value, after we store it, we can just plot the each value here. So with the other code running, we can also see the result that. So you can see the result of the visualizing the graph of the discrete random variable, which is very easy thing. So there's nothing. So there will be no difficulty in understanding this part here. And the next R code is about binomial distribution. So as you can see, we skip the expectation or variance for discrete random variable here. So yeah, the first distribution, which is related to the discrete random variable, is binomial distribution, which is very famous in among any other distribution, discrete random variables. So the first thing is the binomial distribution. So we usually deal with this binomial distribution when we have some event, which is independently, which exists independently, and we see its result from repeated like repeated trials. So when we deal with that kind of event, we usually use the binary distribution. So the density for the binary distribution is usually here. So you can see this formula. So what we have to do for now is just realizing this formula in our code. So this is about n combination x, and the other formula is also for the density. So we can say that x has each discrete value from 0 to n. So we can use this formula in our programming. So we can also set our n or probability, success probability, and the number of the tire. We can set each parameter here. And after we set each parameter, we can get density for along with the parameter by using the formula here. So this part is just for n combination x. So we use the factorial function for getting the combination value here. And the other part is just for this part. So we can also get the p power x and also the 1 minus p power n minus x, which is the same as this part. So because we have each parameter and formula, we can see that we have y value as 0.38 as the density from each parameter here. So when you want to get the probability where where the number of the tire is 3 and success probability is 0.8, we usually get the probability as about 0.38 for getting the 2 success from total of the 3 tires. So this is just one case for getting the probability. Then how about what if we want to get all of the situation, all of the density from each situation? Then it will be easier for us to use some function in R programming. So when you want to make a function in R programming, we use this kind of grammar, which is about making a function in R programming. So with the function command and some argument as our own demand, we can make our own function, which is not already in our programming. So we want to get the probability of our own argument from our own argument, and as we get the result from the return value in here. So when we use this binom underbar p function, we always get, and with any argument n or p or x, we can get the each density and each probability from our own parameter by using this function. So sorry for the inconvenience. And so as we made our function here, so we can designate the argument as our own end. So we can get the same density here. So it means that by using this function and each value, which depends on the situation, we repeatedly get each probability from our situation. So when you want to, so we can fix the total number of the tire and the success probability, and we can differentiate each tire of our own. So, and we can also store each success with each probability into our own variable, whose name is P0 to P3. And then after storing all the value in one vector, whose name is or underbar P, we can see the result here, so which is same as here. And as I already said that if we are dealing with a discrete random variable, all of the summation of all of the probability has to be 1. So we can see that the all possible probability from all of the random variable is 1 here. So the result is right here. And then we can also plot, visualize the result here. So you can see that the probability is like this graph here. And this is what binomial distribution is, and this is how we can get the probability from the binomial distribution. So actually, for getting the density here, we made our own binom underbar p function here and use it along with our own situation. But however, actually our programming already gives us the inner function, which is a d binom. So which means that we don't have to make our own function, and what we have to do is just to use the original function in R programming. So which is very easy thing. So what you have to do is just setting the hyperparameter in the binomial function for getting the probability of the binomial distribution. So instead, with the binomial function and this argument, we can get the same value with the result from our the function that we already made for us. So we can say that these two functions gives us the same value, the same result. And if we use the two value in one vector, we can also get the same value as the result. So instead, for getting the probability of the binomial function, we don't have to make our own function, and what you have to do is just using the binomial function here. So the next is that the CDF function. I don't know if you already learned about this kind of notion, but CDF function is just about summing the result from summing all the probability. So yeah, so let's say that we want to get all the probability when the x is 0 from 0 to 2, then because we are dealing with a discrete random variable, what we have to do is just get the summation value from the value from x, the value of when x is from 0 to 2, which is 0 and 1 and 2, so, which means that after we get each probability, we just sum all the value of what we did with here. So which is same as the situation where we use the binomial function here and sum all the result from the binomial function, which is the same result here. And for getting which is the CDF value here, summation, which is same as the summation of all the value when x is so less than equal to our own value. So however, sometimes it is also we can also feel burdensome for getting all the probability and sum all the value. So in this situation we can also use the p-binomial function here, which help us to get and sum all the density of what we said. So with this parameter q as 2, we can also get the same value from summation of the order value when x is from 0 to 2. So when we have to get the CDF value, it means that it is the time that we can use the p-binomial function in our programming. And so to sum up it, so there are 4 kinds of the R function dealing with the binomial distribution. So when you want to get just the probability or density, we can just use the binomial function here. Or when you want to get the CDF value of the binomial function, we can use the p-binomial function. And this lower tail option is just about the direction. So when you want to get the probability of our random variable is less than or equal to our some target value, we use the lower tail option as true, like this one. However, with other direction, like this one, we use the lower tail option as false. So because we are usually dealing with the CDF value, which is the probability when our x is less than or equal to our target value, we usually use the lower tail option as true. So this is how we use the p-binom function here. And let's say that we want to get the quantity value from the binomial distribution. In that case, we also use the lower tail option as true with the q-binom function. So let's say that we want to get our target value when the order probability is equal to 0.488 with this hyperparameter NMP, then the function gives the result as the 2, which means that if we sum all the probability of the x from 0 to 2, the probability summation of all of the probability is up to 0.488, which is the q-binom function gives us as as the result. So as you can see, the p-binom function and q-binom function is kind of relationship, inverse relationship to each other. So you can notice that. And for our binom function, it gives us the random sample of the binomial distribution. So with this the hyperparameter and n is equal to 10 means that we want to get the 10 sample from this our binomial distribution when our total number of the trial is 3 and success probability is 0.8. So if we run this code, you can see the result that we get the 10 random sample from the binomial distribution. So actually, although we used our own formula for getting the probability, or even we made our own function in our programming, but actually it is not important because our programming already gives us each function for dealing with a binomial distribution here, like the binom, p-binom, q-binom, our binom function, which is the most important thing in this week. So please keep this in your mind. So let's go to the example number 1 here. So there's a success probability which is 0.3, and it says that the total number of the trial is 58. So I use the this hyperparameter as this one, and the number 1 says that the probability of the x is equal to 10 in this situation, which is same as the result of the d-binom function when the x is 10 and n is 58, and success probability p is equal to 0.3, which is done 0.011. So which is very easy. And the second question is that the probability that 30 or more people will be treated. So it is the same as the probability x is greater than or equal to 30, the probability. And actually this is the same as 1 minus the probability when x is less than or equal to 29. So because the summation of all of the probability of the random variable has to be 1. So for getting this probability, we can also result from the other direction from 1. So it will be more convenient for us to use this formula here because we are always dealing with a p-binom function here. So it will give us the answer here. And as I already said, if we set the lower tail option as false, we don't have to deduct the result from 1 and just use the result directly for our answer. So when you set the lower tail option as false, the result will give us the same value from the previous code. But actually, this is somewhat somewhat can be confusing things. So I recommend you use this formula because the default setting for the lower tail option is true, which is the same as the CDF value. So after we get the p-binom function with the default option, we just deduct the result from 1 for getting the right answer. So for the question number 3, what we have to get as the probability is the probability when x is greater than 2 and less than 7. So actually, this is the same as the probability when x is less than or equal to 6 minus the probability when the x is greater than or equal to 1 it is 2, sorry. So it is the same as using the 2 result from the p-binom function here, which is this result. So we solved all the problem here, and yeah, that's it for the binomial distribution. And the next thing and the last thing for this week's class is Poisson distribution, which is also famous in the statistics. So Poisson distribution is usually used when we deal with a count number. So yeah, when we usually deal with a number of events in some specified intervals, then we usually use a Poisson distribution for dealing with that case. So when we deal with the Poisson distribution, we usually have to set one hyperparameter, which is a lambda. So this is when you deal with the Poisson distribution, we always need one hyperparameter, which is lambda, and the density formula is this one. So you can also get the density by realizing the formula with our programming here. So because we already set the lambda is 5, this is per instance, and we want to get the probability when x is equal to 3. So lambda power and exponential function like this one, and x factorial, and divided by the factorial of the x, we can get the density of the Poisson distribution, which is this one here. And as I already have done before, we can also make it by using the function here. So we can use the function as I was the previous thing. So we can also plot along it each x value and each y value, each probability. So as you can see, we can also see that the summation of all of the probability is almost 1. It has to be 1, but because we only use the when x is equal to from 0 to 20, not the infinity, so we get almost the 1, not exact for 1. So, but this is not error. So you can say that even though we use the 20 value of x for the first time, we can get the probability which in which the summation of the probability is almost 1. Sorry. And okay, so as we already have done in binomial distribution, although we made our own function here, Actually, our programming also gives us the Poisson function, which gives us the probability of the Poisson distribution. So let's deal with example number 2 here. So it is just nothing but getting the probability when x is equal to 3. So it is same as using the Poisson function when our argument is 3 and 5 here, which is same as the previous function. And this is about getting the probability when our x is greater than 3. And as I already said, it is the same as the value that 1 minus the probability when x is equal to 0. X is less than or equal to 2. So this is what I did here. Yeah. Actually, it is same as summation of all the probability when x is from 0 to 3. So you can see that the 1 minus sum here is this value. However, as I already said, if we use the p Poisson function is actually the same as similar to the p binom function. It also gives us the CDF value of the Poisson distribution. So we can also get the same result by deducting the result of the p Poisson from 1. So it gives us the same value from the previous formula, previous code. And as I already said, if we set the lower tail option as false, we can directly use the result of the p Poisson function here, which is the same as the previous functions. But as I already said again, I recommend you use the lower tail option as true because it will be more convenient for us to use the CDF value itself. And it is also the lower tail option. It is also the fact that the lower tail option is default value, so we don't have to care about the lower tail option anymore if we concentrate on the CDF value. So if we focus on the fact that we always use the CDF value, we don't have to care about the lower tail option. But if you feel more convenient for using the lower tail option as false, you can also use this function, but yeah, it's on your own. So just choose what you want. And the number 3 is about the probability when x is greater than or equal to 1 and less than 7. And it is also same as the probability of the x is less than or equal to 6 minus the probability when x is greater than or equal to 0. So this is why I use this formula here. So with the argument of lambda as 5, I use the p Poisson function here and deduct the result from the one. So from the other thing. So this is the answer of the number 3 here. And the number 4 is that the question number 4 is that the probability that x is 10. But you have to be careful about the fact that we use the unit hour as 10 because in a question the unit hour was an hour, so we use the lambda as the hyperparameter as 5 when our unit hour is 1 hour. However, in this question, the unit hour is 10, so we have to multiply 10 with the lambda value, which leads to 50. So when we want to get the probability when x is equal to 10, you have to be careful that we have to use the lambda value as 50 here. So this is the reason I use the lambda as 50 when I want to get the probability when the x is number 10. So this is the same as this value here. So sometimes you can see some not number, just programming numbers. When you see that thing, please use this command for getting the numerical number, not the programming number. So it is on your own. And to sum up it, as well as the binomial distribution, there is also the Poisson and P Poisson, Q Poisson, R Poisson function here for dealing with the Poisson distribution. So with the hyperparameter lambda, we always get the density or CDF value or quantile value, and even the random sample from the Poisson distribution with this board function. So I'll explain it once more in Korean. 네, 그래서 오늘은 결국 바이노멀 디스트리뷰션이랑 포화성 디스트리뷰션을 배웠는데요. 사실 저희가 이렇게 플롯도 그리고 뭐 이거 포뮬러 이용해서 덴시티도 구해보고 뭐 이것저것 좀 해봤는데, 사실은 결국 제일 중요한 거는 어차피 R 프로그램에서 이 네 가지 펑션을 준다는 거예요. D 바이노 펑션은 probability, P 바이노 펑션은 CDF value, 그러니까 X가 얼마보다 작거나 같을 확률을 다 더해주는 값을 주는 거고, Q 바이노 펑션은 quantile value를 주는 거고, R 바이노 펑션은 이제 바이노멀 디스트리뷰션의 랜덤 샘플을 주는 거죠. 저희가 원하는 크기만큼. 그래서 사실 앞에 것은 거의 저희가 이해를 돕기 위해서 실습을 해보는 거고요. 플롯이든 포뮬러든 펑션이든 결국 뭐 과제에 있어서나 평소에 이제 통계학을 다룰 때나 제일 간단하고 제일 중요한 것은 이 네 가지 함수를 잘 다룰 수 있느냐. 그럴 때 저희가 평소에 n이랑 p를 잘 설정할 수 있어야 되고요. 저희의 목표에 맞게 x랑 q, p나 n 같은 이런 설정 값들을 잘 넣어주는 것이 제일 중요합니다. 그렇기 때문에 문제가 어떤 것을 지시하시는지를 잘 봐야 되고, 그걸 맞춰서 뭐 하이퍼파라미터나 아니면 저희가 원하는 세팅 값을 잘 넣어서 문제를 해결하시면 간단하게 풀립니다. 그리고 아까 말했지만 p 바이노 펑션을 다룰 때는 로열 테일 옵션이라는 게 있어요. 그게 뭐냐면 로열 테일 옵션이 단순히 저희가 이거를 CDF 밸류라고 하는데, 저희 랜덤 베리어블 x가 저희 타겟 밸류인 스몰 x보다 작거나 같을 확률을 알려주는 게 CDF 밸류거든요. 데피니션상. 이걸 배웠는지는 잘 모르겠는데 아마 곧 배우게 될 겁니다. 안 배우셨더라도. 어쨌든 이거를 CDF 밸류라고 하는데, 이거를 궁금할 수도 있잖아요. 사실 이게 저희가 랜덤 베리어블 다루는 이상 1에서 CDF 밸류를 뺀 거랑 같은데, R 프로그래밍에서는 이걸 어떻게 하냐, 위쪽에서는 로열 테일 옵션을 true라고 둬요. 왜냐하면 이렇게 디스트리뷰션이라고 했을 때, 이게 우리가 타겟 밸류라고 했을 때 결국 여기 있는 probability들을 다 더한 셈이 되잖아요. 그래서 이걸 로열 테일 옵션을 true하고 뒀다는 의미가 되는 거고, 이게 CDF 밸류의 정의 자체가 되기 때문에 훨씬 자연스럽습니다. 그렇기 때문에 이런 확률을 구하게 되더라도 사실 그냥 우리가 평소에서 했던 펑션을 이용해서 1에서 빼자, 그게 더 쉽다는 뜻이었습니다, 저는. 그래서 아니면 로열 테일 옵션을 false로 둬가지고 이걸 f로 둬가지고 그냥 이 확률을 직접 구해도 되고요. 아니면 디폴트 밸류인 true로 둬가지고 그냥 1에서 빼도 되고, 뭘 하든 정답이 되고 그냥 편하신 대로 하시면 됩니다. 그리고 이게 바이노멀 펑션을 다룰 때의 네 가지 함수였고요. 예제 해결했었고, 그리고 여기서도 포화성 디스트리뷰션을 다룰 때 똑같습니다. 종류가 사실 D 포화성, P 포화성, Q 포화성, R 포화성 펑션이 있는데 하이퍼 파라미터만 잘 설정해주면 나머지는 저희 문제 상황에 맞게 density를 구하고 싶은지, 아니면 CDF 밸류를 구하고 싶은지, 퀀티 밸류를 구하고 싶은지, 아니면 랜덤 샘플을 그냥 얻고 싶은지에 따라서 적정한 함수를 쉽게 잘 사용하시면 될 것 같습니다. So I just explained for the summarization of today's class, and I hope that you understand all the things for today's lesson. And yeah, have a good day. Thank you.